Welcome back. We have solved the whole family of bias circuits with algebra. Write the loops, push the numbers through. Today we add a second pair of eyes, the graph, and we start with a twist. Look at this transistor. Its current gain, beta, is not given to us. In every problem so far, beta was handed over. Here it is missing. But it is not really missing, it is hiding in plain sight, printed on the transistor's own characteristic curves. Our job is the usual three numbers: the base current, the collector current, and the collector-emitter voltage. To get them, we will meet two characters. The first is the device, the transistor's output curves, which show everything the transistor itself can do. The second is the circuit, a single straight line, the load line, that captures everything the resistors will allow. The operating point, the one place the transistor actually settles, is wherever those two agree. Picture two lines on a chart crossing once. The device says, I can be anywhere along my curve. The circuit says, I can be anywhere along my line, and only their crossing satisfies both at once. Let us find it. Here are the transistor's output characteristics. Each curve is the collector current as the collector-emitter voltage changes, and there is one curve for each base current, 10 microamps, 20, on up to 50. Notice the shape. Each one shoots up fast, then flattens into a plateau and stays there. That flat plateau is the active region, where the transistor acts like a current source set by the base. And here is the gift. On the flat part, the collector current is simply beta times the base current. So to find beta, we do not need a data sheet. We read it straight off the graph. Take the 40 microamp curve. Follow it across to its plateau and read the collector current, 20 milliamps. Beta is just the ratio, 20 milliamps divided by 40 microamps. 20 over 40 is 1/2, and milliamps over microamps is 1,000, so beta is 500. The curves handed us the gain. Now we can solve the circuit. Now the algebra, starting with the base side. Walk the base loop from the supply down through the base resistor, across the base emitter junction, and down through the emitter resistor to ground. In words, 20 volts minus the base current through 330K, minus the usual 0.7 across the junction, minus the emitter drop. The one subtlety is the emitter. The current there is not the base current. It is beta plus 1 times bigger, the base current plus the collector current it controls. So the emitter resistor, felt from the base, acts like 501 times 200 ohms. Add that to the base resistor, 330K, plus 501 times 200, which is about 100K more. Together, roughly 430K. The driving voltage is 20 minus 0.7, which is 19.3 volts. So the base current is 19.3 volts over 430K, about 45 microamps. A tiny base current, exactly what we expect for a base fed through such a large resistor. With the base current and beta in hand, the collector current is immediate. Collector current equals beta times base current, 500 times 45 microamps, which is 22.5 milliamps. Now the last unknown, the collector-emitter voltage. Walk the output loop this time. From the supply, down through the collector resistor, across the transistor, and down through the emitter resistor. The collector resistor drops 300 ohms times 22.5 milliamps, which is 6.75 volts. The emitter resistor drops 200 ohms times the emitter current, and the emitter current is essentially the collector current, about 22.5 milliamps, so that is 4.5 volts. The collector-emitter voltage is what is left of the 20. 20 minus 6.75 minus 4.5, which is 8.74 volts. There it is, the algebra's answer for the operating point. 22.5 milliamps at 8.74 volts. Now let us see that same answer appear on the graph through the load line. Go back to the output loop, but this time solve it for the collector current as a function of the collector-emitter voltage. Rearranged, the collector current is the supply minus the collector-emitter voltage, all over the sum of the two resistors, 300 plus 200, which is 500 ohms. That is the equation of a straight line, and a line needs just 2 points. First, imagine the transistor fully off, cut off. No collector current, so no drop across the resistors, and the whole 20 volts appears across the transistor. That is the point 20 volts, 0 milliamps on the right. Second, imagine it fully on, saturation. The collector-emitter voltage collapses to 0, and the current is just the supply over the two resistors, 20 over 500, which is 40 milliamps. That is the point 0 volts, 40 milliamps up top. Connect those 2 points and you have drawn the load line. Every operating point the resistors will permit, all on one straight stroke. Now bring the two characters together. The device gave us the family of curves. The circuit gave us the load line. Lay the line right on top of the curves. The transistor must live on its curve, and it must also live on the load line, so it sits exactly where they cross. Which curve? The one for our base current, 45 microamps, sitting between the 40 and the 50. Follow the load line until it meets that curve and drop down to the axes. You land at 8.74 volts and 22.5 milliamps, the very same numbers the algebra gave us. That crossing point has a name, the Q point, the quiescent operating point. It is the handshake between the device and the circuit, the single state where the transistor obeys its own physics and the circuit's voltage law at the same time. 2 methods, 1 point. Let us gather it up. We were handed a transistor with no beta, and we read it straight off the output curves. 20 milliamps over 40 microamps gives 500. Then the base loop gave a base current of 45 microamps. Beta times that is a collector current of 22.5 milliamps. And the output loop left 8.74 volts across the transistor. Finally, we drew the load line, cutoff at 20 volts, saturation at 40 milliamps, and watched the Q point appear exactly where the line crosses the 45 microamp curve. The headline to carry: the operating point is where the device meets the circuit. The curves are the transistor's personality. The load line is the circuit's demand. The Q point is the one place both are honored. And with that, our DC tour of the bipolar transistor is complete. Next, we meet a different breed entirely, the field effect transistor, where a voltage, not a current, takes command. See you there.